US Physics Olympiad, year 2014, USAPHO. Final exam. Problem B2. In parts A and B of this problem, assume that velocities v are much less than the speed of light c, and therefore ignore relativistic contraction of length or time dilation. Part A. An infinite uniform sheet has a surface charge density sigma and has infinitesimal thickness. The sheet lies in a xy plane. Question 1. Assuming the sheet is at rest, determine the electric field E, magnitude and direction above and below the sheet. Question 2. Assuming the sheet is moving with the velocity v in the direction x parallel to sheet, determine the electric field E, magnitude and direction above and below the sheet. Question 3. Assuming the sheet is moving with velocity v in x direction, determine the magnetic field B, magnitude and direction above and below the sheet. Question 4. Assuming the sheet is moving with velocity v in z direction perpendicular to the sheet, determine the electric field E, magnitude and direction above and below the sheet. Question 5. Assuming the sheet is moving with velocity v in z direction, determine the magnetic field B, magnitude and direction above and below the sheet. Part B. In a certain region there exists only the electric field E in form of Ex plus Ey plus Ez and no magnetic field, as measured by an observer at rest. The electric and magnetic fields E' and B' as measured by observers in motion can be determined entirely from the local value of E, regardless of the charge configuration that may have produced it. Question 1. What would be the observer electric field E as measured by an observer moving with velocity v in direction z? Question 2. What would be the observed magnetic field B as measured by an observer moving with the velocity v in direction z? Part C. An infinitely long wire on the z-axis is composed of positive charges with a linear charge density lambda, which are at rest, and negative charges with the linear charge density negative lambda, moving with the speed v in the z direction. Question 1. Determine the electric field E, magnitude and direction at points outside the wire. Question 2. Determine the magnetic field B, magnitude and direction at points outside the wire. Question 3. Now consider an observer moving with the speed v parallel to the z-axis, so that the negative charges appear to be at rest. There is a symmetry between the electric and magnetic fields, such that the variation to your answer to part B can be applied to the magnetic field in this part. You will need to change the multiplicative constant to something dimensionally correct and reverse the sign. Use this fact to find and describe the electric field measured by the moving observer, and comment on your result. Some familiarity with the special relativity can help you verify the direction of your result, but is not necessary to obtain the correct answer. Solutions. Question 1. Assuming the sheet is at rest, determine the electric field E above and below the sheet. Solution. Due to symmetry, this electric field must go out of sheet from both sides, and using Gauss cylinder we can make the equation. If cylinder has a base area A, we have this equation that 2E multiplied by area equal to charge inside of this cylinder, which is sigma A over epsilon 0. And from here we have magnitude for electric field is sigma over 2 epsilon. And direction, we have a positive direction in above the sheet in Z direction, and negative below the sheet, like here. Question 2. The motion is not affecting electric field. It means that the answer will be the same as for question 1. Question 3. Assuming the sheet is moving with the velocity v in x direction, determine the magnetic field B above and below the sheet. Solution. Assuming that v greater than 0, the right-hand rule indicates there is a magnetic field in the negative y direction for z greater than 0, and in positive y direction for z less than 0. From Ampere's law applied to a loop of length L normal to x direction, we have this equation to determine what is a magnetic field B. To get the right-hand rule, note that in time t, an area VTL moves through the loop, so a charge sigma VTL moves through. Then the current through the loop is sigma VL. Applying symmetry, we have this solution for magnetic field. Question 4. Assuming the sheet is moving with velocity v in z direction, determine the electric field E above and below the sheet. Again, the motion does not affect the electric field, so the answer is the same as that for question 1. Question 5. Solution. Applying Ampere's law and asymmetry, there is no magnetic field above and below the sheet. Interestingly, there is no magnetic field at the sheet either. Consider an Ampere loop of area A in the xy plane as the sheet passes through. The loop experienced a current of form this one. But the loop also experienced an oppositely directed change in flux of the form this one. So the right-hand side of Ampere's law, including the displacement current term, remains the zero. Question 1. What would be the observed electric field E as measured by an observer moving with the velocity v in z direction? Solution. In part A, we showed that if the electric field was produced by a sheet of charge, then it was unaffected by the motion of an observer. Thus, in general, E prime equal E. Question 2. What would be the observed magnetic field B as measured by an observer moving with the velocity v in z direction? Solution. No magnetic field was created by the motion of the sheet of charge in the direction of the electric field. So the magnetic field in the frame of reference of the moving observer should likewise not depend on the component of the electric field in the direction of motion. When the sheet of a charge was moving in the positive x direction, a magnetic field was created in the negative y direction. The observer moving in the positive x direction is equivalent to the sheet of a charge moving in the negative x direction, creating a magnetic field in the positive y direction. That is, an electric field is in the z direction causes an observer moving in the x direction to observe a magnetic field in the y equal z cross product with x direction. Furthermore, the magnitudes of the fields satisfy equation B equal mu 0 epsilon 0 V E, or we can replace mu 0 epsilon 0 with a 1 over c square. That will be this expression. Combining this with the previous equation, we have B prime equal negative 1 over c square multiplied by cross product V and E, which is this expression. Part C. An infinitely long wire on the z-axis is composed of a positive charge with a linear charge density lambda, which are at rest, and negative charges with a linear charge density negative lambda, moving with the speed v in the z direction. Question 1. Determine the electric field E, magnitude and direction at the points outside the wire. Solution. The wire as a whole is neutral, so there is no electric field outside the wire. Question 2. Determine the magnetic field B at points outside the wire. Solution. The current in the wire is I equal lambda V. So Ampere's law yields that B equal this expression, mu 0 multiplied by lambda V over 2 pi r in the tangential direction. The current is in the negative z direction, so by the right hand rule, the circular B field lines would point clockwise, looking in that direction. Question 3. Now consider an observer moving with the speed v parallel to the z-axis, so that the negative charges appears to be at rest. There is a symmetry between the electric and magnetic fields, such that variation to your answer to part B can be applied to the magnetic field in this part. You will need to change the multiplicative constant to something dimensionally correct and revise the sign. Use this fact to find and describe the electric field measured by the moving observer, and comment on your result. Some familiarity with the special relativity can help you verify the direction of your result, but is not necessary to obtain the correct answer. Solution. The result of part B was B prime equal negative 1 over c square multiplied by cross product V and the electric field E. Exchanging the electric and the magnetic fields, reserving the sign and fixing the dimensions, we have electric field E prime equal cross product V and magnetic field B. Taking the cross product yields an electric field vector that points outward with the magnitude lambda over 2 pi epsilon 0 r multiplied by v square over c square.